Hello everyone, welcome to Chapter 18, Planar Kinetics of a Rigid Body, Work and Energy. In this module, first we will start with kinetic energy for a rigid body to discuss what is the difference between a rigid body and a particle when it comes to kinetic energy. Now, the kinetic energy of a rigid body can be expressed as the sum of its translational and rotational kinetic energies, meaning that, first of all, similar to a particle, the kinetic energy, if you remember, used to be half mv square. For a rigid body, now we have half mvg square. The only thing that we add here is g as the center of gravity for that object. Since it has dimensions, so which point do I take the velocity? Every point in that object might have a different velocity, so we take the velocity of the center of mass or the center of gravity. We also add to it the rotational kinetic energy. So in this form, for the rotations, instead of velocities, we have angular velocity, W, or omega, sorry. And the equivalent of the mass for rotational effects is the mass moment of inertia, Ig. And therefore, we end up with half Ig omega square. So this shows you the kinetic energy in equation form for a body in general plane motion. What do we mean by general plane motion? That the rotations and the velocities are happening in the 2D plane, and this is the equation that we get. Now, we want to discuss this for different cases. First of all, let's assume we have a case of pure translation. So we have an object as the one shown on the right. It is a large object that has dimensions, and I have a velocity for the center of mass or center of gravity shown here, and this velocity is equal to the general velocity. It's one velocity for all the points, meaning that I have no rotations. In this case, the rigid body is subjected to only curvilinear or rectilinear translation, a velocity that could be either in a curved path, could be in a straight line, and the rotational kinetic energy now becomes zero. So this is zero, and I end up only with translational effect. So this becomes similar to a particle. It's the same as the particle kinetic energy that we discussed in previous modules. Now, what if I have a rotation about a fixed axis? So I have the object shown on the right. As you can see, it is rotating about the fixed point O. In this case, I have a rotation around this point. Now, remember from kinematics of a rigid body that the relation between the velocity of the center of gravity and the angular velocity equals to Vg equals to Rg times omega. This is something that you already know, so keep this in mind. Now, let's go to the expression that we discussed. Kinetic energy will equal to half mvg square plus half Ig omega square. Now, when I solve problems, I want to minimize the number of unknowns. In this case, I have Vg unknown could be, I have omega could be unknown. So instead of writing them as two unknowns, I already know a relation between them. So I will rewrite the velocity in terms of the angular velocity. And I end up with half. Take omega as a common factor. You will end up with Ig plus, which is here, plus mrg square. Okay. Also, you know that Ig plus mrg square, or in other forms that you've seen it before, Ig plus md square, is basically the parallel axis theorem. And this gives you another format for t equals to half Io omega square. Now, this is not a derivation. I'm not saying that this is the form that you need. I'm saying that you can use either this form or you can use this form. You can do it in one of the two ways. That being said, because usually you could have in the problem given to you Ig, and then you have to add mrg square. Sometimes you are given Io around the fixed axis of rotation, or if you know the form of Io the direct form for IO, then you can use it directly. So you can use either one of those two. Now, there are cases where the rotation occurs about a mass center G. So the center of mass G is the same as the center of rotation. For example, I could have something like this. I could have a disk, okay, that is fixed in its own center. So in this case, this is point O, which is the same as point G. In this case, I only have T equals to half Ig omega squared. Because if you go back to the previous equation, R in this case is 0, and you end up only with Ig. So that's why if the center of mass and the center of rotation coincide, they are the same point, you only have half Ig omega squared. The final case is when we have general plane motion, meaning that the object is moving with a certain velocity, and at the same time it has an angular velocity, and it's not fixed to rotate about a certain point. So the general expression is the same. Kinetic energy equals to half mvg squared plus half Ig omega squared. Now, if you want to reduce this to something similar to this expression, I'm saying this just for the sake of discussion, but this is something that we usually do not practice. If it arises in a certain problem where you want to reduce it to this format, then as you remember from the instantaneous center of zero velocity when you discussed the kinematics of a rigid body, that the instantaneous center of zero velocity represents a fictitious center of rotation for the object in a general plane motion. So if you happen to know where this instantaneous center of zero velocity, then you can reduce the kinetic energy for a general plane motion to this format. But generally what we use is this expression right here. That's the one that we use for a general plane motion. So let's have one example where we discuss the different types of kinetic energy and we try to find them. The system shown of 3 elements consists of a 6 kilogram block B, a 10 kilogram disk D, and a 12 kilogram cylinder C. If no slipping occurs, determine the total kinetic energy of the system at the instant shown. Now, before we start calculating these energies, let's analyze the system. Block B, as you can see, is moving downward, so this is pure translational motion. If you look at disk D, this is a disk that is fixed at its own center of mass, so it is rotating around its own center. So I have pure rotation where the center of mass and the center of rotation are the same. And finally, cylinder C has general plane motion because it is moving with a velocity as well as rotating as it moves. So it has 2 components. Now let's start computing the kinetic energies of the system. We will start with VB. Okay. Now I know that the kinetic energy can be related for computed for these. So first I want to find what are the relations between also the velocities and the angular velocities. I know that the relation of the velocity of block B, I can use it to find omega d, since in this problem only the velocity of VB is given. So I know that VB equals omega d RD. Right? So substitute the values. So this equals to 0.8 should equal to RD equals to 0.1 omega d, and this will give me that omega d should equal to 8 radians per second. Now I need to find the velocity Vg of cylinder C, and I need also to find the angular velocity for cylinder C, omega c. So to do this, first of all, I can say that the velocity of this point E should equal the velocity at this point. These two velocities are the same. So I can relate the velocity from the right hand side. I can say velocity of that point equals to the velocity of I can do on the right hand side the velocity of E. So therefore VE, which we will get it from disk D, should equal to omega C. Now I cannot say RC because this is not pure rotation. Now since it says there is no slipping, then you know that from kinematics that the instantaneous center of zero velocity in this case becomes the point of contact with the ground, which is this point. Okay, so it's going to be omega C R CIC. Okay, now the velocity of E, now let's look at it. Velocity of B is given as 0.8. So it follows this cable. 0.8 is following this cable. It enters the disk because it's pure rotation at this point with the same velocity, and it comes here also with the same velocity, which is the same in the same cable. Since it is only one cable, then the velocity at the cable is the same everywhere. So this gives me that this is 0.8 should equal to, now RCIC, as I mentioned, that this is translation as well as rotation. So this is general plane motion with no slipping. So the IC is at the point that meets with the ground. So I'm going to say the distance, or RCIC, becomes twice the radius. So 0.2 times omega C. And this gives me that omega C should equal to 4 radians per second. Okay. Now I need to find the velocity of the center of mass of cylinder C, which is point G. And I can do this by saying also Vg equals to omega C RGIC. So Vg should equal to 4 multiplied by 0.1, which is the radius. And this gives me that Vg should equal to 0.4 meters per second. Okay. Now, what we are left with is to find the kinetic energies of the system. So I found the three velocities. I'll start now calculating the energies. So first of all, I will start with block B. So it is very easy. It is translation, so it's going to be easily half mb vb squared, which will equal to half the mass given as 6 and the velocity given as 0.8, and this will give me 1.92 joules. Now we will do the disk D. So we have TD, this is pure rotation, so it's going to be half I. So again, this is pure rotation, so I only have the rotational kinetic energy, so it's going to be half ID for disk D, that means at its own center of mass, omega D square. So this will equal to half. Now, ID for the disk, as you may know, is half mr squared. So it's going to be half. Don't confuse the half and say there's only one. One half is for half I omega square, and the other half is for the I itself, the mass moment of inertia. So it's going to be half md rd square times omega d square. So this equals to half multiplied by half multiplied by the mass, which is 10, multiplied by r square, which is 0.1 square, multiplied by omega d, which is 8 radians per second, so 8 square. And this will give me that Td equals 1.6 joule. Now, for the cylinder, you can see the diagram shown to the right. This is general plane motion. VE comes from the block, it's the same. So I have VG shown also here. As you can see that the IC, you can find it using the triangle from here. So I'm going to have two components, VG as well as omega C. So I'm going to say for cylinder C, so TC should equal to, write the general expression first. I'm going to have half MC for C multiplied by VG for C square for cylinder C plus half IC, okay, around its own center of mass, omega C square. So this should equal to half M VGC square. I'm not changing anything here. Now I want to open the mass moment of inertia for the second part. So it's going to be half, and then for the disk, again, it's half mr square. So it's going to be half mc, let's see in here, r c square, okay, multiplied by omega c square. So let's plug in the numbers. The first one is going to be half multiplied by the mass, which is 12, multiplied by the velocity, which we found to be equal to 0.4 square. So this is the first part, plus half multiplied by half, multiplied by the mass, which is 12, multiplied by RC square, and R equals to 0.1, okay, multiplied by omega C, which equals to 4 radians per second square. And this will give me 1.44 joules. Finally, the kinetic energy will equal to TB plus T for the disk plus T for the cylinder. And if you add all of these, you get up the final answer, 4.96 joules. So it's good when we start going into solving problems for the principle of work and energy or conservation of energy, always compute these kinetic energies separately, and then at the end you just add them all together. Now, the second part of this module is how to find the work done by a force. Now, this does not change greatly between particles and rigid bodies, but we will go through it for the sake of having all of these in one module. First of all, to remind you that the work done by a force is the force multiplied by the distance traveled by the object moving in the same direction of the force component. So if an external force acts on a body, the work done by the force when the body moves along the path S, as shown in the figure, is defined as the work equals to integral of F dr. This is in a vector format. If you open it in a scalar format, becomes F cosine theta ds. So this is the general definition. Now, if I want to apply this into actual cases, I could have a constant force, so force does not change with the distance. In their case, the energy the work done by the force becomes F cosine theta times the distance S. Okay. Now I could have other types. I could have the weight done by the work done by the weight. Now, if the weight of a body does work, is when the center of mass undergoes vertical displacement. I don't care about other points. It has to be the center of mass that is moving, or center of gravity. So if the displacement is upward, and you know that the force of the weight is acting downward, then the work is going to be negative. If the displacement is downward, then it's going to give me positive work because the force of the gravity is acting downward, which is the same direction of the displacement. Therefore, we write the work done by the weight as minus W delta Y. Now, if delta Y is positive, meaning that the object moved upward as shown in this example, then this is going to give me negative work. If the displacement is downward, so delta Y will be negative, the negative will cancel with the minus sign shown here and will give me positive work. For a spring, remember that I have two locations. The object or the body moved from location 1 or position 1 to position 2. So for a linear spring, the work will be negative because the displacement of the body is always opposite to the direction of the force. And think about it. If you have a spring and you push it with your hands, you can feel that the spring wants to push back to return to its position. If you stretch the spring, you can feel the force of the spring wants to compress it to get it back to its position. So the force is always opposite to the displacement. Now, the work done by the spring equals to minus, then you open a bracket, and this is a source of a common mistake. It's a minus sign, and then you open the bracket. Half k is 2 square minus half k is 1 square, you close the bracket. Another source of a mistake is a general confusion for students. What do we mean by S2? What do we mean by S1? First of all, the subscript 1 and 2 refers to the position 1 and position 2. And the definition of S is the amount of stretch or the amount of compression. Therefore, if I say S2, then I mean this is the amount of stretching or the amount of compression of the spring at position 2. Therefore, I can compute S2 by saying it is the current length of the spring at position 2 minus the unstretched length. So I can say that S2 equals L2 minus L0 and S1 equals to L1 minus L0. Now, why is this confusing? Because some problems will tell you that the spring at position 2 is compressed by, let's say, 0.5. Then you do not have to do these subtractions. What you have to do is just use 0.5 as your S value directly. This is the source of the confusion. So, with this, we have to discuss just a few things about forces that do not do work. There are some external forces that do not do work. For instance, reactions at a fixed support, they do not do work because the displacement of that point is 0. So, for example, if I have something like this, I do have some reaction forces here, okay? And these forces do not give me work because this point is fixed. Also, same thing can be happen here. I have these forces at the support do not give me any work. Also, internal forces do not do work because they always act in equal and opposite pairs. For example, if I have a rope and I cut the rope and I want to see the tension inside the rope, we're not talking about external forces like this, but when you cut the rope and see the internal tension, they will be opposite and equal in magnitude, so they do not give me any work. Also, normal forces and friction forces acting on bodies as they roll without slipping, again, rolling without slipping over a rough surface do not do work. Because remember, if you have rolling without slipping, it means that this point is the instantaneous center of zero velocity, no motion. Therefore, the friction force will not give me any work because that point is not moving. And also the normal force usually does not give work because it is normal to the surface of motion. So it does not give me any work. Now, finally, the last thing is the work of a couple moment. So if I have a couple moment as shown in the figure to the left, for example, I have the force F shown here with the distance r between them. So when a body is subjected to a couple moment or a couple force that gives me couple moment, it experiences general plane motion, and the two couple forces do work only when the body undergoes rotation. So you can have the moment done by these forces will give you the work because it's going to force the object to go under rotation. Now, when the body translates, the positive work of one force cancels the negative force of the other one. So this F is going upward, this F is going downward. They are opposite in direction, and the displacement is going to be the same. So they are going to give negative and positive work, and they cancel, so you don't have to consider that one. So if the body rotates through an angular displacement d theta, as shown in the figure in the bottom here, then the work of the couple moment, I can do the integration similar to the work done by a force. Instead of saying integral of S1 to S2, it's going to be theta 1 to theta 2 of m d theta. So it's theta 1 to theta 2. If the moment is constant, the couple moment is constant, does not change with theta, then basically you get a constant expression. So it's going to be m multiplied by theta 2 minus theta 1, which we've done the same for a force, a constant force acting on the body. Now let's take an example on how to calculate the work done by different forces. The bar shown in the figure has a mass of 10 kilogram and is subjected to a couple moment m equals to 50 Newton meter as shown in the figure. And also it has a force of 80 Newton, which is always applied perpendicular to the end of the bar. This is a very interesting statement. So the force 80 Newton is always perpendicular to the end of the bar as shown in this figure. Also, the spring has an unstretched length of 0.5 and remains in the vertical position due to the roller guide at B. So the spring is always going to be vertical. Determine the total work done by all the forces acting on the bar when it has rotated downward from theta equals 0 to theta equal 90. So I have two locations. The first one, if you could imagine, this is the bar. So this is location 1, and then it rotates until it reaches 90. So this is position 2. So I want to find the work done as I move from position 1 to position 2. So first of all, let's start with the weight of my object. First of all, let's draw a free body diagram showing all the forces so I can identify what do I have. Let's say generally at any point, this is my bar. I do have reactions here because it is fixed at this point. So this point is A, so we have AY and AX. Okay, I have the center of mass here is going to give me a weight acting downward. So this is the weight acting downward. Okay. Usually write all the forces before you think about do they give me work or what kind of work do they give me. Just write everything. This is the weight. I have the perpendicular force at the end of the bar, which is P. Okay. And I also have the spring force acting upward. It's always a vertical force as mentioned in the problem statement. This is the spring force. Now, let's look at the distances from here to here. This is 1.5. You can see it here in the problem. So this is 2 meters. Center of mass is in the middle. So it's going to be half and half between the two. This is 2 meters up to here, and you have 1 meter here. So half of it here will give me 1.5, which is what we have in this problem. Now, what else do we have? The spring force is going to be applied here. So it is 1 meter away from this end, and it's going to be 0.5 away from the center of mass. Okay, so the distance here is 0.5 and the distance here is 1. So I have all the distances with me. Now let's look at the weight, the work done by the weight. So U, W. Now The bar was at zero at position 1, so it was theta was 0, and it moved down. So the weight is acting downward, and the center of mass acting moved also downward. Therefore, I'm going to have a positive work done. So it's going to be 9. It's going to be the weight multiplied by the displacement. So the weight is 9.81 multiplied by the displacement. So let's think about this and look at the problem. The bar was like this, okay? Then it moved down, it rotated until it reached this point, okay? Center of mass is located here, so this distance is 1.5, and it moved up to here. So this distance is also 1.5. Therefore, if you look at the amount of vertical displacement, it equals to 1.5. So it's going to be the weight, 9.81, the gravity times the mass, which is 10. The mass is given as 10, so this is mg. This gives me the weight, multiplied by the displacement, which is 1.5. And this will give me the work done, which equals to 147.2 joules. So this is the work done by the weight. Now we can do the couple moment that is applied. We forgot to add that one. So we had the moment that is applied also here. I forgot to add it. So we have the work done by the couple moment. Remember, this is a constant moment, so you only have to do m multiplied by theta 2 minus theta 1. So it's going to be m, the moment, which is 50 newtons meter. So it is going to be 50 multiplied by theta. Now, theta, don't do the mistake of using degrees. Don't say 90 minus 0. You have to do it in terms of radians. So at 0, you have 0. At 90, you have pi over 2. So it's going to be pi over 2 minus 0 is basically pi over 2. And this will give me 78.5 joules. The next force that we have here is the, we can say, the pin reactions. So the work done by the pin reactions at A, let's say A reactions. This is equal to 0. Again, if you remember, because we said the work done by reactions is 0 because they do not have any displacement at the point. So this is equal to 0 because AX and AY are applied at point A, and point A is a fixed point. Okay, so we move on. The next thing we have is the spring force. Now, look at this. The spring force, I know the distance. Where is it located? Now, what I need to do first is to find the spring amount of stretching in the spring. Look at the problem. It says that the spring has an unstretched length of 0.5. Therefore, I need to find the spring length at position 1 and position 2. At position 1, you can see that the length is going to be from here to here, and this equals to 0.75. At position 2, the spring is here. Remember, it is located a distance of 0.5 from center of mass. So the length here is 2. Sorry, this is 2. So the distance between point B, in this case, is going to be 0.75 added to the 2. So it's going to be 2.75. So let's go back to my spring. The spring stretching when theta equals 0 and theta equals, so at, first of all, theta 0, I know that S1 equals 2. the current length 0.75 minus the unstretched 0.5 gives me 0.25 meters. And at theta equals 90, S2, remember S is the current length minus the unstretched length. It's very simple once you know the definition of these things. So the current length, as we said, is 2.75 minus the unstretched of 0.5 gives me 2.25 meters. Therefore, I can write the work done by the spring force equals to, remember there's a minus, then you open a bracket, you have half, spring constant is given as 30 times S2 square. So this is 2.25 square minus, inside the bracket, half 30 multiplied by S1, which is 0.25 square, and this should give you the final value for the work done by the spring force, and it is equal to 75 joules. Okay. Finally, and this is the minus sign. I forgot to add the minus. Remember that the work done by the spring force is always negative. So this is minus 75. Now we want to do the work done by the force P, okay, which is always perpendicular. Now, the force P, if you look at it here, it used to be here, and now it is here. So it is related to the rotational movement of the bar, but the force P has to be multiplied by a distance. So I can relate theta with S. I can find I know that it moved from 0 to 90 degrees, from 0 to pi over 2. So I need to convert this into a distance. And we convert this by the relation that S equal theta times R. Okay. Now, what is the total length? What is R? In this case, it is 2 plus 1, so it is 3. Therefore, I can say that the distance S traveled will equal to theta R. This is the relation between them. So it's going to be pi over 2. So it's going to be pi over 2 multiplied by the distance, which is 3. And this will give me 3 pi over 2, which will be equal to approximately 4.712 meters. And now I can do the work done by the force P. This should equal to the force, which is 80, multiplied by the distance, which is 4.712, and this will give me the answer to be 377 joules. Now, the total work done now is basically you add all the work done by the forces, by the work done by all the forces. So you have 147 that we did here, and you have the 78.5. So 147.2 plus 78.5 minus 75 plus 377. This will give you a final answer of 528 joules. And this covers a variety of forces that gives you work, and it's a good practice to go through this yourself and try to calculate these all over again. With this, I will conclude this module, and make sure that you go through it carefully before you go to the next 2 modules that discusses the principle of work and energy and conservation of energy. I hope that this was useful to you, and I wish you the best of luck with your studies. Thank you all.